Welcome to this explainer. Today, we're diving straight into what is essentially a high-stakes financial thriller, one that's unfolding right now in the semiconductor industry. We are going to unpack the brutal, multi-billion-dollar race to 2-nanometer chips. It's a wild story, really, where incredible, mind-bending engineering breakthroughs are colliding head-on with cold, hard market realities.
So let's just tackle this provocative question right out of the gate. What actually happens when the world's most advanced microchips become too expensive for the world's richest companies? Because you see, the abstract physics of shrinking transistors down to the literal atomic level is now crashing violently into the real-world economics of consumer tech. We're hitting a wall where making chips smaller and faster isn't just an engineering nightmare anymore. It's a massive financial hurdle, and it's one that even trillion-dollar tech giants are seriously struggling to clear.
Section 1. The Silicon Battlefield. Racing to volume production.
To really wrap our heads around this trillion-dollar paradox, we first need to look at the fierce foundry rivalry happening right this second. This timeline here shows you the intense urgency of the situation. TSMC is aggressively pushing to hit volume production of their N2 node by the fourth quarter of 2025. But right on their heels, Intel plans broad market availability of their 18A Panther Lake processors, ramping up from Fab 52 in early 2026. And looking just a bit further out, the enhanced TSMC N2P process will start delivering its first chipsets by late 2026. The margins for error here? Well, they are practically non-existent.
Moving to Section 2, the foundry face-off, Intel 18A versus TSMC N2.
This super tight timeline builds into an incredibly complex architectural showdown between these two heavyweights. Now, look closely at the density versus power delivery trade-off we're showing here. TSMC is boasting a massive 313 million transistors per square millimeter, compared to Intel's 238 million. But Intel is risking absolutely everything to level the playing field. They're introducing two major innovations at the exact same time, combining their new ribbon-FET gate-all-around transistors with a completely new way to deliver power.
Okay, so the crucial point to understand here is that while Intel's approach frees up super valuable real estate on the front of the chip, which effectively helps close that density gap we just talked about, producing this power delivery network on the backside costs a lot more money. You literally have to flip the wafer over during manufacturing. The whole shebang means Intel's 18A process is likely going to be much more expensive to fabricate than TSMC's traditional front-side approach.
Section 3, the Apple compromise, trillion-dollar choices.
And this skyrocketing cost of innovation brings us perfectly to the actual consumer impact. It shows how even the absolute wealthiest tech giants are being forced to compromise. I mean, rising wafer and memory costs are threatening to chew through profits so aggressively that Apple is allegedly being forced to split their upcoming iPhone 20 chips. Industry reports are suggesting that to protect their margins, Apple will likely keep the standard A21 chip on the older, relatively cheaper TSMC N2 node, and then reserve the highly advanced N2P process exclusively for the high-end A21 Pro. Now, that specific compromise makes perfect financial sense when you realize the newer N2P successor only offers a measly 5% performance improvement at the same clock speed over the standard N2. Just 5%. For a company like Apple, with their absolute mastery in chipmaking, they can easily make up that 5% gap through architectural tweaks on the standard A21, rather than coughing up the massive premium for the newest manufacturing node across their entire product line. Section 4, the price war, the $300 barrier. But hey, Apple isn't the only one feeling the squeeze here. Let's look over at the ultra-premium Android market. $300. That is the shockingly high rumored per-unit price for Qualcomm's upcoming Snapdragon 8 Elite Gen 6 Pro chipset. Qualcomm has already openly admitted they're implementing a double-digit percentage price hike because of rising supplier costs. Just think about what that means for smartphone makers for a second. Handing over $300 just for the brain of the phone, and that's before even factoring in screens, cameras, memory, or batteries. Our wallets are literally already crying. And as you can see, Qualcomm's massive price tag seriously risks alienating their customers. But it blows the door wide open for their rival. MediaTek's Dimensity 9600 Pro is rumored to launch at roughly $216. Guys, that's a massive 28% cheaper alternative for phone makers who are already backed completely into a corner by these rising component prices. MediaTek is just capitalizing beautifully on this financial strain.
By partnering early with TSMC on the enhanced N2P process for late 2026, they're bringing some massive improvements to the table. We're talking an 18% performance jump or a 36% power reduction compared to the previous N3E generation, plus a 1.2x increase in logic density. They are essentially offering top-tier, cutting-edge 2-nanometer performance to the masses, but at a much more palatable price point.
Finally, Section 5, the future frontier, beyond 2 nanometer. Okay, so while 2 nanometer is today's super intense battle, the war for the future is already being mapped out. Looking at the research presented at the 2026 VLSI Symposium in Hawaii, we see clear evidence that this industry absolutely refuses to slow down. They are rapidly pushing the boundaries past the 2 nanometer hurdle. We're talking mind-bending concepts here, like 3D stacked FETs from Samsung, ultra-high-density 3D flash memory targeting over 1,000 layers, and entirely new circuit architectures specifically designed to push the AI frontier forward. And this futuristic talk, it is completely grounded in actual real-world science. Take a look at these microscopic images. They show brand-new transition metal dichalcinogenide materials, specifically tungsten diseleniide and molybdenum disulfide, being engineered right down at the atomic scale. Engineers are having to look far beyond traditional silicon to find materials that can actually handle the extreme, intense demands of next-generation transistors.
And the optimizations happening on current layouts are equally staggering. Advancements like TSMC's high-density SRAM, which was also presented at the symposium, prove that engineers are successfully squeezing every single drop of efficiency out of these microscopic designs. Achieving over 37 megabits per square millimeter while using just 2.28 picojoules per access, that just shows that the drive for energy efficiency is every bit as relentless as the drive for raw speed.
So, as we wrap up, I want to leave you with this final thought. As the innovation versus cost paradox just continues to escalate across the global supply chain, something eventually has to give. Will these corporate compromises, like using slightly older chips in standard phones or shifting to more affordable foundries, actually protect your wallet? Or are our consumer electronics about to get a whole lot more expensive as the massive bill for the 2 nanometer war finally comes due? Thank you so much for joining me on this explainer. Keep your eyes on the silicone, everyone, because our entire digital future depends on it.